Okay, so my name is Alain Tchana. So I'm from Cameroon, but I live in France where I do my research. So as you probably know, so Cameroon is the heart of the world. Okay, so we are in the center of Africa, and it's the heart of the world. So today I will present this work. So it's about backpressure mitigation in multi-tier application or microservice applications. So this is a joint work with Brice, Djob, Renaud, David, and Daniel. So the main author of this work is Brice, so he was not able to have the visa in time, so I have to present the work. Okay, so this is the motivating example of this work. So here we have an example of two typical multi-tier applications. So this can also be applied to microservice-based applications. So imagine we have, so at the top, on the top of this figure, so we have an e-commerce application. So we have here final clients who can send some requests to the application. So this is the application which is located inside the data center. So this is a three-tier application. So the load balancer receives the request, and then forward the request to a web server, which can send the request to a database or a file server to extract some data, okay? And we have the return path, right? So we have another example for a Zimbra application. So we have the same kind of architecture, okay? So what is important here is to observe that we have different tiers, okay? And the protocol between two tiers are not always the same. So they are different protocols. So when we analyze these applications, we can observe that for some return values, so that we call final payload, so they are not used by intermediate servers. Okay? So for example, imagine your mail server. Okay, you want to retrieve a mail. So the mail is located here. So you send the request, your client send the request to a load balancer and then the IMAP server, and here the mail server here. So you extract the mail, your email, or some attached files, and this file will go through these servers, but will never be neither read or modified by these servers. Okay? So this is what we called final payload. So the problem is by relaying this final payload, we offload some loads on these intermediate servers. Okay? And this is not necessary. So what we want to do is to avoid relaying this final data. So if we know that we have some data here, that will not be modified or read by these servers, we can bypass them. Okay, so this is the basic idea. So the problem, so when we relay this data, as I mentioned, you have, so this is a simple micro benchmark. So we have a three-tier application, okay, with a front end, an intermediate server, and a backend, okay? And the backend just services some files, static files. And we have another experiment with spec mail and spec web, okay? So what we can see, so this is the CPU load on the different servers. So the different tier, the front end and the intermediate server and the backend. So we can see that for this application, the server which really does the work is the backend, but the load, the CPU loads, is mainly located on the intermediate server and the front end. Okay? So this is a problem because it makes scalability quite difficult to implement for this kind of application. So this is an example, another experiment which show on the same application, so the three-tier application, we want to observe, so the first tier which will saturate, okay? So we have the same application, the front end, the intermediate server, and the back end. And we can observe on this curve that the first tier which saturates is the front end. So in order to scale the application, we need to first scale the front end, which does not make sense, okay? So we want to avoid this problem. So this is why we came up with this technique that we call DISC, so distributed shared TCP connection between several applications or several tiers in a multi-tier application. So what we want to do is what I mentioned. If we know that some data will not be used by the intermediate servers or the front end, we want to directly send the data from the back end to the same TCP connection which has been established between the client and the front end. Okay? So we use the same TCP connection, but we want to share this connection with another server. So by this way, we can offload, we can reduce the CPU loads on these servers. So this is not the first work which tried to address this problem. So the main approach behind existing solutions is what we call connection handoff, okay? So we have DSR, distributed, you know HTTP DSR, so it's a well-known technique to offload or to migrate a TCP connection from one server to another server. You also have this solution, CRAB or Prism or Quick DSR and a version of DSR for Quick. So all these techniques or these solutions cannot address the problem that we want to address here because their limitations is like this. So they are only able to bypass one server, which is the load balancer. So in our case, we want to bypass several tiers. So we can have n tiers here. In microservice application, for example, when you look at Alibaba traces, you can have a chain which include 40 microservices. Okay, we want to bypass all of them. So this is the first limitation of existing works. And the second one, it is mandatory for this solution that all the tiers use the same protocol, HTTP. So in our case, as you can see in this application, so between these two servers, they use HTTP, but here it's another protocol. It's a different protocol. Okay? And the last limitation of this solution is that they entirely bypass the load balancer, which is not good because sometimes we implement inside the load balancer the way to do a smart and an intelligent load balancing techniques because we want to retrieve some statistics, okay, at that level. So we don't want to bypass the load balancer. So our solution is, so first of all, we consider that a response can be organized in terms of a header, a payload, and a footer. And we only want to bypass the payload, okay? The header and the footer will flow through the traditional, the normal communication path. So it's quite simple, the idea is quite simple, but we want to do it without modification for the clients, the external clients. We can modify it, okay? As I mentioned, we want to bypass only the payload. We don't want a lot of modification inside the application. We want to support all application level protocols. Also keep the same security level for the storage. We don't want to expose the storage, the database to internet, okay? And finally, we want to support TLS. Okay, so our solution is just a new simple protocol which lies between TCP and the application level protocol. Okay, so we use several techniques. So first of all, BPF for kernel modification. So I will present quickly. So we want to intercept the communication between the client, the external client, and the load balancer, and forward the request to the backend, or modify the backend to directly send the request to the client, but using the same TCP connection. So we do it at the kernel level using BPF. We do act redirection because, as I mentioned, the header and the footer will flow the same communication path. So the load balancer will still receive the ACK, TCP ACKs from the client. Okay? If we want the backend to send data, we need to send the ACKs to the backend. Okay? Also, we have to control TCP sequence number generation, and finally support TLS. So we do this by implementing a distributed version of TLS sessions. So this is the workflow, so how the application, our system works. So first of all, when the client, the external client establishes a connection with the front end, we can, we save the connection identifier into a key value store inside its BPF map, inside the kernel. And then, as soon as the client sends a request to the front end, so the front end, so each intermediate tier will decide if this request, so the response, can be bypassed. So we can configure the bypass by using, for example, if I can say that for this size of payload, we can apply bypass because it makes sense to bypass. Okay? And then we send the request. So if bypass is decided by this server, so this server says that I can be bypassed for the return value, for the response. So it adds a new header to the request. And we do the same for the intermediate server. And at the backend level, so it decides finally if we really need to bypass because it has the payload. Okay? And if it's the case, so it sends the header. So the header goes through the front end, and the front end can now here, so he can identify the previous connection and say, okay, for this connection, we have to bypass the payload. And then it sends the header to the external client, and the client will, so after this, so the front end can ask the back end, now you can send the payload directly to the client, but using the initial TCP connection. And then the backend will just create raw packets and send the packets to the client. Okay? The client will respond with ACT, so the ACT arrives here. Then we need to translate the TCP sequence number because the client, the TCP sequence numbers here maintained by the front end is not the same on the back end. So we need to do some translations, okay? Then we send the ACT to the back end so that the back end can continue sending the packets and increase its TCP window. And at the end, when the back end sends all the data, then the front end can send the footer. That's it, okay? So you can see the paper, we generalize the idea, so any components here can play the role of a client or a backend. So if an intermediate server, for example, this one, modify or accesses the payload, it becomes a backend for this specific payload. Okay, so I will not give this detail, you can see the paper. So we implemented our solution in Linux, as I say, with BPF, and also using several applications, so traditional multi-tier applications, okay? And yeah, the results are quite simple. So we are able to offload the CPU from the intermediate server and the front end. That's good. So it's perfect for scalability. Now the backend can scale easily. We don't need to scale the front end. And that's it. So you can read the paper. So in conclusion, we have these techniques that works and you can use it. And I want to finish with this slide. So contact me if you want to work in France, if you want to drink some Guinness or eat some cheese. So I'm free.